We are continuing our discussion of regioselective enolate formation in Chapter 17, considering how things are different when you make an enolate under reversible conditions versus not. Recall that last time, for a molecule, a simple ketone like this, we noticed that there are two different kinds of alpha protons, both with similar pKa's. And we noted that if you use a weak base like ethoxide, where the pKa of the corresponding conjugate acid is around 16, you don't expect very much enolate to form, but you can get enough to do chemistry. And the question is, of the two possible enolates, which forms in larger amounts? And the answer is the more stable one. And we talked about how that the more stable enolate is the more substituted one. And the reasons why the more substituted enolate is more stable have to do with the same reasons that more substituted alkenes are more stable that you learned in 351. So even though we don't have very much enolate under these conditions using a weak base like sodium ethoxide, most of the enolate that does form is this more stable enolate. Your text will sometimes call that the thermodynamic enolate, and that's just a fancy way of saying the enolate that is more stable. Okay? And we can do reactions, as I said, even though there's a very small amount of enolate that forms, a huge percentage of our material is still starting material, we can take advantage of Le Chatelier's principle and do reactions on the very small amount of enolate that's present, and most of our product should come through the more substituted enolate. All right, let's now talk. We're not even dealing with those reactions yet. We're going to get to them, but we need to address the regioselectivity issue first. Now let's change the story a little bit. Let's say that instead of using a very, very weak base, or a relatively weak base relative to the pKa's of the protons, let's use a much stronger base. So we'll call this regioselective enolate formation under, I can't speak and write at the same time very well. I was going to write enolation for enolate formation. Maybe we should just make that a word. Regioselective enolate formation under irreversible conditions. There's a couple of different ways you can do this. The one that you will encounter most is using lithium diisopropyl amide as a base. And I showed you this last time. LDA as a base is so basic, so strong that with a ketone, with a pKa of around 20, you can expect basically 100% enolate formation. And the reason for that is the pKa of the conjugate acid of LDA is around 40. So the equilibrium constant should favor formation of the enolate by a factor of 10 to the 20, or basically 100%, right? That's what we mean by irreversible. It's 100% yield and there is no going back. When you run reactions under irreversible conditions, it actually does not matter which enolate is more stable. In fact, the only thing that matters under irreversible conditions is which forms faster. And of course, in the example I just showed you above, it's not an issue. The ketone there is simple. The alpha protons on either side are identical. But we'll go back to the example we did above, and the question will be which enolate forms faster. So you recall our energy diagram, how, and maybe I'll copy and paste it, how the enolates were up much higher in energy than the starting material was. We're going to have to adjust that diagram down here to reflect the changes we've just specified. So let's sort of talk through that. Nice. Okay. The enolates are going to stay where they're supposed to be. They're going to stay where they are. We're going to erase the base on either side. We're still going to have this starting material only with a pKa of 20, only our base is going to be lithium diisopropyl amide, or LDA. Okay? And then the conjugate acid, which we're going to draw by the enolate, is just the conjugate acid of LDA, which has a pKa of 40. We're drawing this to remind us sort of how we should rank the relative stability of the starting materials versus enolate intermediates. So under this set of conditions, the base is so reactive, and I'm going to erase that 99% because we're going to need a way to adjust that in a little bit. It turns out now that the starting material here is much less stable than the enolates that form. And again, you can tell that from the comparison of the pKa's. Now it's downhill to form the enolates. You see that difference? That's all because we're using a much, much stronger base. And so under this set of situations, and I'm going to erase the idea of major enolate and minor enolate now too, we need to reassess which one's going to form. And as I said, under irreversible conditions, it doesn't matter which one is more stable or less stable. It just matters which one forms fastest. Okay? So let's think about that and how the structure of the enolate and of lithium diisopropyl amide might influence how fast we think these enolates form. What do you predict is the major difference when LDA sees the purple alpha proton versus the orange alpha proton? Sterics, right? That's the obvious one. The one's on a secondary carbon, the other's on a primary carbon. And that is true. The purple alpha proton is more sterically hindered. That means it is harder for the LDA, which itself is pretty bulky with these isopropyl groups. They're not quite tert-butyl groups, but they're getting there. You expect it to be easier for LDA to approach the less substituted alpha proton. Another way of saying that is that the transition state in which LDA attacks and removes the orange alpha proton is lower in energy than the transition state in which LDA attacks and removes the purple alpha proton. That line is not lovely, but whatever. Okay, so the transition state for removing the purple alpha proton is much higher in energy than the transition state for removing the orange alpha proton. It does not matter that the orange enolate is less stable than the purple enolate, because once we form the orange enolate, it's so tremendously downhill, there's no going back. And that's different. When we do the reaction under reversible conditions, you can form the less stable enolate as many times as you want. You can always go back to starting material and back to the more stable enolate. Yeah?
So is it LDH that makes the reaction irreversible?
LDA, yes, is the base that makes this reaction irreversible. The idea is you're using such a strong base that it's very downhill going to the enolate. Therefore, we get, 100% yield of, we'll call this, the major enolate under these conditions, and your text will call this the kinetic enolate. And your text will call it that because kinetic means how fast does the reaction happen. So this is the enolate that forms fastest. When you do the reaction under irreversible conditions, the only thing that matters is which forms fastest, and it's the less substituted one. Yeah?
I guess I'm just a little confused about why it's 100%, right? Like if these are reversible conditions, then...
I said irreversible.
Sorry, irreversible conditions, yeah. If it's irreversible, shouldn't we still get some of the other stuff?
You're right, and that's why I erased. The question is it really 100%? The ratio of more substituted enolate to less substituted enolate is going to depend on the difference in height between these two transition states. You're right, if it's irreversible, we expect to get some ratio dictated by the relative heights of those peaks. And, but overall, what I meant by 100% is we're not gonna have any of the starting material left. So it's gonna be 100% enolate of some variety, X percentage kinetic enolate, and Y percentage of the more substituted enolate. You're going to be able to assume, of course, the text does not expect you to predict product ratios. So you can assume that the reaction works to give you basically 100% of the less substituted enolate when you're using LDA, even though in practice, when you get in the lab, it is rarely that good. On the other hand, yeah.
Is there a way to control which of these products you get, or is, like you said,
Can you control which of the products you get? Yes, by changing the conditions. So you've seen by this that if I use sodium ethoxide as a base, the majority of the enolate that I have, even though it's a very small amount, is going to be this purple enolate. Whereas if I use LDA, the majority of the enolate that I have is going to be the less substituted enolate. The more, yeah, go ahead.
Is there anything other than sterics that could affect what product you get?
Are there other factors besides sterics?
Like if you have an electronegative atom on one side.
Yes, so pKa still matters, and this is a good question because it leads us into one other way you can deal with, one other way you can take advantage of irreversible enolate formation. So a second strategy for irreversible enolate formation is to use a ketone or aldehyde or ester starting material with an especially acidic proton. So in this beta diketone, the proton, which I'm going to highlight in some color, I don't know, orange is fine, has a pKa of 9. So if I use sodium ethoxide as a base, that's still 100% yield because the corresponding conjugate acid of the ethoxide base is ethanol, which has a pKa of 16, meaning enolate formation there is favored by a factor of 10 to the 7, which is essentially 100% yield. So even looking at this proton, looking at this starting material, even though I have two different kinds of alpha protons, I have some here that I didn't draw, and I have one between the two ketones, it has a lower pKa. That's also irreversible enolate formation. So yeah, you can use, but again, the principle is basically the same, right? Equilibrium constant pKa differences lead to 100% enolate formation. Other questions? All right, so let's get to reactions, and one of the most common ones that we can do on enolates is what we're going to call alkylation. Enolate alkylation. So I'm going to show you enolate alkylation under reversible conditions like we did above, where we're going to get a product that comes from the more substituted enolate. I will also show you enolate alkylation under irreversible conditions, where we are going to get product that comes from the less substituted enolate. And then we'll talk about some practical issues that you'll encounter along the way and some workarounds that have been developed. So a classic example of enolate alkylation, and for now, let's just use our simple diketone that has orange alpha proton that's less substituted, purple alpha proton that's more substituted. If I use sodium ethoxide, NaOET is how we abbreviate that. For those of you playing along at home, NaOET equals the ethoxide anion and then sodium as a cation. And again, the conjugate acid of that is an alcohol with pKa 16. So we expect using sodium ethoxide to be reversible enolate formation. That is, we don't expect there to be very much enolate formed at all. And of that enolate that forms, we expect there to be mostly the more substituted, more stable enolate. So I'm going to draw that as an intermediate here. I'm going to draw it with a negative charge on the carbonyl carbon, but I'm going to also draw the other resonance structure in which the negative charge is on the alpha carbon, okay? And I'm going to understand, even though I've drawn this as though it were a product, we're not actually forming that in a very large amount. However, in a second step, if we introduce an electrophile, an alkyl halide, then we can do what's called alkylation chemistry. So let's just use CH3Br. This is methyl bromide, and this is basically going to be an SN2 step. Now, the problem is that the enolate is nucleophilic both on the carbonyl oxygen and on the alpha carbon. So you sort of have to decide which of those two is going to attack your electrophile. What we observe generally in organic chemistry is that enolates prefer to attack at the alpha carbon. That has to do with some stuff from MO theory. It turns out the HOMO of this molecule is on both the oxygen and the alpha carbon, but there's more of it on the alpha carbon. So you can push arrows for the alkylation reaction just in the same way that you ever did in 351 for SN2 reactions. And the product puts your new alkyl group on the more substituted alpha carbon. So here's the new bond we made, and there's the CH3 group. Okay? Understanding that at any given point we don't have only a very small minor amount. I don't want to use the word minor because this is the major enolate, but we only form a very small amount of enolate. Okay? So that's enolate alkylation. It's regioselective. We use regioselective to describe what happens in a reaction where you could get one or more, two or more different isomers as products, but you only get one. The other possible, what we would call regioisomer, would be if the methyl group here ended up on the orange alpha carbon. All right, questions about that? Yes? Will it ever end up on the oxygen? You would not be wrong to worry about that. For our purposes in the text, you don't have to. Yep. Others? Yes?
So does NaOEG always attack more, like the more sterically hindered hydrogen?
So you've asked, does sodium ethoxide always attack the more sterically hindered hydrogen? The answer is, based on our earlier analysis, no, it would do both in a reversible fashion, but percentage-wise, we've got more of the more stable, more substituted enolate that forms. And so that's where we get most of our product. Yeah, effectively what's happening here is we are, if we were to complete this diagram, we would show this enolate intermediate going on and reacting with methyl bromide to form, that's a poor choice of color, methyl bromide to form the alkylated product. And by Le Chatelier's principle, we're drawing more starting material over the barrier and to the final alkylated product by using that methyl bromide reagent. Other questions? Yeah.
So in a synthesis, would it matter that we're only forming like a small amount of enolate, or does the continuous product doesn't matter what yield we get?
In a synthesis, does it matter that we're only forming a small amount of enolate? No, because when you do the alkylation step, you're using Le Chatelier's principle to pull starting material through this step to a even more downhill step later. Okay, others? Okay, yes?
So someone mentioned like it could form the oxygen.
Right.
Would that be like the methyl group just attaches to the carbonyl carbon?
the carbonyl oxygen, yeah, the question was that the enolate, of course, is nucleophilic both on the alpha carbon and on the oxygen. I explained briefly that enolates generally are more reactive on the alpha carbon than on the oxygen. And that has to do with a result from MO theory that would be difficult to predict with our current level of understanding, but is generally what we see.
So it just looks like the small amount that does form is like a ether with it.
Right, we would actually, the thing that you're worrying about that I'm going to tell you don't worry about is called an enol ether, and they are known, but we're going to ignore them. Okay. Now, among the many things that should be making you uncomfortable in life, there is one here that nobody's mentioned yet. So let me give you a hint. When you were in 351 and somebody wrote these two things together, what would you have predicted the product should be? An ether, right? That's actually called the Williamson ether synthesis. Some of you may do that in the Chem 353 lab. I don't know. That was the one that I spilled all over the counter. So one of the problems with this that in general is glossed over in your text, but that you would be very worried about in a lab would be, if I only form a very small amount of enolate, I still have a ton of sodium ethoxide in solution. And how do I make the alkyl halide react with the enolate instead of with sodium ethoxide? Now, you probably argue that the enolate's more reactive, and it is, but you worry about the potential for this side reaction happening, okay? So that's a clue that maybe sometimes there might be a better way. The other thing you worry about is, even though we're pretending that we live in a world where we get 100% regioselective enolate formation, you would worry about the potential for the formation of this minor byproduct. And again, we're going to pretend like we live in a world where it's not really that big of an issue. Your text allows you to do so, but in the lab, you would be worried about whether you got this one or this one and in what ratio. Okay? So let's now show you how to do this with lithium diisopropyl amide. Again, we're going to assume that it works fabulously, though in the lab there are some concerns that you might have. So same starting material. Same orange alpha proton that's less substituted, purple alpha proton that's more substituted. This time we're going to use lithium diisopropyl amide. There are a few other things that are often included. I sometimes will not write them down, but your text will. Your text will often include THF as a solvent. Do you have to memorize that THF is a solvent? No, you have to know enough not to be distracted by it. THF stands for tetrahydrofuran. It is a polar solvent, and that's important because LDA is an ionic compound. Let's just draw it again in case you forget. It's lithium diisopropyl amide. So THF is a polar solvent. Importantly, it is aprotic, meaning it has no acidic protons. Why would you not want to have acidic protons in your solvent? Because LDA is a very strong base. That's a very silly and expensive mistake to make, right? Your base is consumed before it even sees the reactive material. So polar aprotic solvents are good for dissolving ions, but not protonating bases. The other thing that will often be included is a temperature. Often in your text, it will write minus 78 degrees Celsius. And you might look at that and say, that is strangely precise. Why not just say minus 80? And sometimes it will. Minus 78 cues to the organic chemist's mind that you're doing this reaction in a bath with a flask that's not in a bathtub, but you're doing the reaction is in a flask that is immersed in a bath of acetone with dry ice at the bottom. And the temperature of dry ice immersed in acetone is around minus 78 C. Some people still do it that way. We also have other refrigeration techniques in more modern times, but that just means really cold. The reason you do the reaction really cold is to benefit from the selectivity that I talked about. Remember, when doing the reaction under irreversible conditions, the thing that matters most is which forms fastest. And the thing that determines which forms fastest is the relative barrier heights towards the less substituted enolate versus the more substituted enolate. The reason you want to keep things cold is so that your starting material only has enough kinetic energy to surmount the smallest barrier and gets petered out on the way going up the higher barrier. You could imagine if you heated things up more, your starting material might have enough kinetic energy to go over both of them with similar frequency. Then your product ratios aren't going to be good. So all of that stuff that you can pretend doesn't exist but is really important in the lab, and if you see it in a problem in your text or in a problem on the exam, you need to not be distracted by it, but you need to understand where it's coming from. Under those irreversible conditions, if we do the reaction right, we can expect to form mostly the less substituted enolate, which we can draw in either resonance structure. And then again, in our second step, we will do the alkylation step where we will introduce the alkyl halide. And we will make the new bond. I won't draw the mechanism because you've seen it before above, but here is our new ketone, and the new bond we make is with the orange alpha proton, and the alkyl group goes on the less substituted carbon. And again, we expect that to be our major product. Now, the fact that I've drawn major and minor products up here versus not down here, some people are going to ask, is that significant? No, it is not. In fact, showing the major product alone is sufficient for the top reaction. Showing the major product alone is sufficient for the bottom reaction. To highlight that, we will just erase things and pretend like I was making a point back there, but yeah. Okay. Questions? Lots of hands. So, yes?
Is the cold temperature that's also relevant for not just alkylation, that's just like regular enolate formation?
Cold temperature, is that important? Yes, and you would continue that through. This reaction would occur in the same pot. You'd make the enolate first, and then you'd take a syringe and you'd drip in the alkyl halide afterwards. Others, yeah? Yes?
Okay.
Both of you, you two pick who's going to go first.
Okay, cool. So it seems like there's a pretty good way to make the kinetic version, right? There's like irreversible reaction, you can get a lot
Right.
of from this. And you mentioned that with under reversible conditions, there were like problems with it, and it looks like you get like super low yields regardless. Like, is there a way to overcome that?
Yeah, so the question is, I mentioned the potential for like ether formation, and your text ignores that entirely. You can assume that this one works well, but yes, there are some synthetic workarounds that allow us to do this in a little bit higher yield that we'll talk about. And go ahead, yep.
So this LDA, I just want to make sure I get this right. Is it, that's non-reversible, but the first one, LDOET, is reversible?
That's right. LDA is the irreversible enolate formation, and using sodium methoxide with this starting material is reversible. Essentially, it's a pKa difference. You're comparing the number 20 for a standard pKa of an alpha proton on a ketone to the pKa of the conjugate acid of your base. Here 16, here 40. So that's why LDA is irreversible.
And at what pKa is there like a limit on?
Is there a limit to when it's reversible, when it's not? No, I haven't really defined that. Okay. Others? Yeah.
Just a general mechanistic question is what prevents the, just like in the reversible example, from from attacking the carbonyl-carbon, just like we actually do see?
Right. So a great question is, under the reversible conditions, you have seen NaOET or molecules like it act as nucleophiles to attack the carbonyl carbon rather than remove the alpha proton. And the question is, do I need to be worried about that? The answer is, sure, it's happening, but it is inconsequential. The reason it's inconsequential is if you get to that tetrahedral intermediate where the alkoxide has attacked the carbonyl carbon, there's no good leaving group on it other than the alkoxide group, so it just gets kicked back off. At best, you could protonate on the carbonyl oxygen to make this hemiacetal intermediate, but we've just learned that hemiacetals are really not stable unless they're cyclic. So yeah, you've identified a side reaction that has no consequences. Okay, others? Good. So let me just, to test you out, give you this is the classic, somebody must have done this once and then everybody was like, ooh, that's a good exam question. So I imagine this shows up on lots of standardized exams. Here is a ketone starting material, and we're going to use, we'll use LDA over here. I'm not going to write all the rest of the stuff, and we'll use this alkyl halide here. Over here we'll use sodium ethoxide, and I won't write the other stuff, and then the same alkyl halide. Okay, I'm going to see how much you've been paying attention. You got 30 seconds. Draw both products. Guess what? Now you have 25 seconds. Stop it. Okay, now hold on. I've given you about 30 seconds. You should have at least part of it sketched out. Now, pause, look at what you've written. Now, I want you to talk to somebody next to you and compare your answers. But, people pleasers, do not back down so easily. If somebody else, if the person sitting next to you tells you you're wrong, don't go quietly into that good night, okay? 30 seconds to fight it out. Go. Okay, let's bring it back in. So, tell me, somebody raise your hand, somebody bold, and tell me where do the the 3 carbons of the alkyl halide end up on my product for using LDA? Where am I going to put them? On the less substituted carbon. Good. You know that. Why? Yes. All the stuff we just talked about. But to repeat succinctly, LDA is a strong base. It makes the enolate irreversibly. And so the only thing that matters is which forms fastest. The less sterically hindered enolate forms fastest. And that's the less substituted one. That's where we get the alkylation. So on the other side, where does the 3 carbon unit go? On the more substituted one. Good. Okay. So that's a famous problem in this area. You've solved it. That's good. Make sure you go do some practice to make sure you can solve that on your own. Importantly, if you were wrong, don't look at this and say, okay, I get it now, and move on. Actually take some time to go back and read, re-listen to some stuff, and make sure you get it down. Yeah?
Does the propyl for the LDA reaction prefer a certain carbon on that ring?
Does the propyl group in the LDA reaction prefer a certain carbon on that ring? The answer is that the alpha protons are billions of times more acidic than any other proton on the ring. So the only carbons we worry about are the two alpha carbons, because their pKa's are around 20, whereas the other protons' pKa's are in the 50s. Yep. What else? Somebody else? Yes? No? Yeah. Do we need to worry about stereochemistry in products? Thank you for asking that. Notice that we, in two cases, have made a stereocenter. The answer here is somewhat complicated, but if, as a first approximation, if you look at the enolate, the alpha carbon of the enolate is sp2 hybridized planar. That means it can attack the alkyl halide from either above or below, meaning if you make a stereocenter, you're going to get both configurations. Now, the reason I said it was complicated was because technically we have a stereocenter here. Right? You see in this molecule how where the methyl group is, purple alpha carbon is a stereocenter. I didn't show you the stereochemical configuration here. In this product, you would have 4 potential diastereomers, 2 sets of enantiomers. Enantiomers have to be formed in identical ratios. Diastereomers do not. So I can't say that everything would be formed with equal configuration. That being said, you can assume that an enolate should be alkylated from above and below at similar rates. Over here, we only form one stereocenter. You would have to get both enantiomers. The fact that I've shown these without dashes or wedges should communicate to the astute reader that you have both configurations possible. Yeah?
Can enolates do like hydrogen shifts?
Can enolates do like carbocation rearrangement? No. Yep. Others? Yes?
So in conclusion, we need to know that it is possible to form the two, but we don't need to. Would you for example, have us draw them out? Or
So it would be fair for me to draw, for example, this product. It would be totally fine for me to draw this product like this. 1, 2, 3. And then draw the other one. It would be fine to take a similar approach here and draw all 4 of the possible stereoisomers. It's easier just to do it this way. Yeah. Okay, what else? Okay, so sometimes we talked about some potential problems in enolate alkylation. One of the most important was the possibility that your ethoxide base might react with your alkyl halide. Another issue is sometimes, despite your best efforts, the selectivity between the major and minor enolates, major and minor products, is not that good. And so sometimes we need a workaround that is more likely to be highly effective. So I want to show you now what that workaround that's presented in your text is. There are 2 things. We're going to talk about them both at once. These strategies are named somewhat ineptly, I think. One is called the malonic ester synthesis. I say it's named ineptly because this molecule, malonic ester, is actually the starting material and not the desired product. So I suppose this could have been better said, the synthesis of alkylated enolates using malonic ester as a starting material, but that's less of a ring to it, I suppose. So they call it the malonic ester synthesis, but it is the synthesis that starts with the malonic ester. Similarly, there is a very related synthetic strategy called the acetoacetic ester synthesis, which really means you're not making acetoacetic ester. Again, that is starting material. Why didn't I just draw the arrow up? That would have been so much easier there. Look at all the class time we're saving by doing that. All right. So Let me illustrate this with an example. Suppose your starting material were a ketone and you wanted to just use sodium ethoxide because it's cheap, and you wanted to do enolate alkylation, and you were using a simple starting material which only had one kind of alpha proton anyway, so you anticipated that the regioselectivities were not a problem. And suppose then you made this one by putting the methyl group on one of the carbons of acetone. And then supposing you wanted to go further and put another methyl group on using the same set of reaction conditions. Again, sodium ethoxide and CH3Br in a second step to put a second alkyl group on that more substituted alpha carbon of your ketone starting material. Okay? So this is, we call this product an alpha-alpha dialkylated ketone because on the alpha carbon here are two alkyl groups that weren't there to begin with. Using the assumptions that your text gives you, we're going to basically assume that that works great. But as I've tried to point out, sometimes the selectivity between the purple enolate and the orange enolate isn't as good as you might hope. And other times, you worry about the potential for your base starting material to be a nucleophile and react with your alkyl halide. So a solution to that is these two strategies, the malonic ester synthesis and the acetoacetic ester synthesis. And it's going to give you the same product, but we're going to use a different starting material, and it's going to be a bit of a challenge. So what I'm going to do is I'm going to highlight in gray the carbons that were present in the original starting material, and then I'm going to show you this alternative approach, and I'm going to highlight the corresponding carbons that are present for this alternative approach. So this molecule is called acetoacetic ester. It is an example of a beta keto ester because there is a ketone on the beta carbon relative to the ester. And I'm going to show you a set of conditions whereby we can convert this same acetoacetic ester, this acetoacetic ester into this same product. It's going to involve basically identical reactions, but then something else. So first, we're going to deprotonate that alpha carbon using sodium ethoxide. Ketones that are, alpha protons that are adjacent to two carbonyls have really low pKa's. This pKa is around 13. So you expect sodium ethoxide to be able to completely deprotonate it, and then we're going to add an alkyl halide. Then we're going to do it again. I'm going to just highlight the reaction first, and then we'll deal with mechanism. Once we've got the first alkyl group on, we'll deprotonate again and then alkylate again. Notice that in the product, the ester carbon is gone. Where did it go? And this allows us to introduce something that happens a lot with beta keto type esters and acids in biology. It's called decarboxylation. It's where you lose CO2. At this stage, we add an aqueous acid, so water and hydronium, and importantly, we add the fire triangle, or heat. And as part of that step, we are going to both hydrolyze the ester, and second, we're going to lose CO2, which in chemistry, when you lose CO2, We're going to call that decarboxylation, because we like words that end in A-T-I-O-N, decarboxylation. So if you're wondering, where did that ester carbon go? We lost it as CO2. And this is an important time to talk about it because we'll see biology use decarboxylation all over as a strategy. All right, let's get through as much of this mechanism as we can. In the first step, the ethoxide base completely 100% removes the proton whose pKa is 13. That proton is in between two carbonyls. So we make this enolate in 100% yield. This is an example of quantitative enolate formation or irreversible enolate formation. And it's because ethoxide is such a strong base relative to the alpha proton. The next step is simply the SN2 alkylation reaction, where we make a new bond between the purple alpha carbon and the methyl group of the alkyl halide, and we break the carbon bromide bond, and Br- is the leaving group. Notice the genius of this step. You don't notice it, but remember what I told you was the potential if there's still sodium ethoxide around by the time we introduce the alkyl halide. We worry about the specter of ether formation. And you are welcome, for those of you out there that noticed I just gave you a Halloween costume idea. I am the specter of ether formation, fear me, ooh, right? Nobody's gonna do it, but go ahead. I was waiting for that. Is there extra credit if I go as the specter of ether formation for Halloween? No, but I would really, really like to see it. I'll like your Instagram post. How's that? Okay. So notice that this method, by the time we get to introducing the alkyl halide, there's absolutely no sodium ethoxide present, because we have consumed 100% of it by deprotonating this proton, so deprotonating that alpha carbon. So there's no ethoxide present. We get really efficient alkylation. At that stage, we still have another proton present whose pKa is again 13. So in our, this was step 1, this was step 2. Step 3, we introduce ethoxide again. Again, we remove just that proton and we get this enolate. There is another scary ghost that we just dodged a problem with. Nobody's mentioned it, but did you notice this ester and that nucleophile? Why do you think they're similar in structure? What are we trying to avoid? Go ahead. Right, if you attack on the ester, nobody's asked, but you could have asked, does ethoxide ever attack the carbonyl carbon of the ester? The answer is sure, but it's inconsequential. Notice what happens if it does. You have two of the same leaving group. One of them gets kicked off. You can't tell which. So that is we have thwarted the side transesterification reaction. So two evil ghosts defeated today. The ghost of the specter of undesired ether formation and the specter of undesired transesterification. All right, we will continue on with that on Wednesday. Have a good week. I'll see you then.